Let's start with a very practical problem. Suppose a company receives thousands of customer messages every week. Some messages are about delivery, some are about billing, some describe a bug, some are from customers who may be about to cancel. If a human team had to read all of these messages one by one, the workflow would be slow and inconsistent. Text classification is one way to make this workflow more systematic. The key idea is simple. We take a piece of text and we assign it to one or more labels that we have already defined. But the important point is not just the label. The important point is what the label allows the system to do next. For example, if the text is, "My invoice was charged twice," the useful output is probably not an essay about the customer's feelings. The useful output might be billing issue. If the text is, "The app crashes every time I export the report," the useful output might be bug report. And if the text is, "This is the third time this happened, I am done," the useful output may include escalation or churn risk. In each case, the model helps because it changes what happens next. On the slide, you can see this as a pipeline. A customer text goes into a classifier. The classifier produces an actionable label. Then that label can route the message, prioritize it, or escalate it. So a classifier is not just describing language. It is turning language into a decision that a workflow can act on. A useful way to think about this is that the label set defines the model's decision space. If the available labels are bug, billing, delivery, and churn risk, then the model can only choose among those possibilities. It cannot invent a better workflow for us. We choose the possible answers first, and then the model chooses among them. There are a few common shapes for this. In binary classification, there are two labels, such as spam or not spam. In multi-class classification, there are several possible labels, but each text gets one of them, such as billing, delivery, or bug. In multi-label classification, one text may receive several labels at the same time. That last case is often important in real products. A message like, "I want to cancel after the checkout bug," is not only a bug report, it is also a churn signal. If we force the system to choose just one label, we may lose information that matters for the business. This is why labels become workflow commitments. If we create a label called refund request, someone needs to decide what happens after that label appears. Does it go to support? Does it create a ticket? Does it trigger a retention playbook? In many cases, classification is partly a machine learning problem and partly a product design problem. So the first practical rule is this. Before choosing the algorithm, define the decision. What should the system do when it sees this kind of text? Once that is clear, the labels become much easier to reason about. And that brings us to the next question. What should those labels actually mean? One common mistake in classification projects is to treat labels as if they are just names. We might write down labels like bug report, feature request, complaint, and churn risk, and assume the task is now defined, but a label name is only the beginning. The harder question is where the boundary of that label is. For example, suppose a customer writes, "The new dashboard is confusing and I may switch providers." Is that a complaint? Is it product feedback? Is it churn risk? A reasonable person could say yes to more than one of these. That does not mean the example is useless. It means the example is doing real work. It is showing us where the label design is ambiguous. In supervised learning, examples teach the boundary. On the slide, the green points might represent one label, the pink points another, and the yellow points the ambiguous cases in between. The model is learning from these examples. But if the examples are inconsistent or if the label guide is unclear, the model will inherit that confusion. This is why a good label guide matters. A label like bug report might mean something does not work as expected. A feature request might mean something should exist but does not yet exist. A complaint might mean the customer is expressing a negative experience. These definitions do not need to be perfect, but they should be concrete enough that two people would usually label the same example in the same way. A practical label guide usually has three small parts. It has an include rule, when should this label be used? It has an exclude rule, what looks similar but should not receive the label. and it has a few edge examples. For churn risk, an include example might be, I am planning to leave. An exclude example might be, I am annoyed today, if there is no sign of cancellation. The edge examples are especially useful because they make the boundary visible. Here is the naive workflow. Collect text. Ask people to label it. Train a model. The better workflow adds a review step. When labelers disagree, do not just average the disagreement away. Ask what the disagreement is telling you. Maybe the example is a boundary case. Maybe the label guide is unclear. Maybe a missing category should be added. This is especially useful in business settings. Easy examples can go directly into the training set. Disputed examples can go to a review queue. Over time, the review queue improves the label definitions, and the label definitions improve the model. This loop is not just quality control, it is how the team learns what the task really is. At the beginning, you may think you have 4 labels. After reviewing real examples, you may discover that 2 labels overlap, or that one important label is missing. That is normal. Good classification projects often improve the task definition before they improve the model. One useful mental model is this. The model should serve the label design, not compensate for a confused one. If humans cannot explain what a label means, the model may still produce predictions, but those predictions will be hard to trust. So a practical recipe is, first define the workflow decision, then write short label definitions, then collect examples, and then review disagreement. Try this with one of your own text workflows. Take 3 labels you might use and write one sentence for what each label means. You will often find that this step reveals the real design problem before you train anything. Now we can look at sentiment analysis, which is a familiar classification task that has exactly this problem. Sentiment analysis is one of the most familiar examples of text classification. The labels are usually simple: positive, neutral, and negative. Sometimes we use more detailed labels, such as frustration, satisfaction, urgency, or uncertainty. The goal is to turn attitude into a signal. This can be useful. A product team may want to know whether feedback is becoming more positive or more negative after a release. A support team may want to prioritize messages that sound frustrated. A marketing team may want to compare sentiment across product categories. The output is easy to understand, and that is why sentiment analysis is attractive. The naive version is to treat sentiment like a mood meter. Positive is good, negative is bad, neutral is in the middle. That can be fine for a dashboard. But if the output drives an action, we usually need a more careful interpretation. Negative sentiment from a loyal customer may be a repair opportunity. Neutral sentiment from a silent customer may not tell us much at all. The label is a signal. The workflow decides what the signal means, but the language is not always simple. Look at the sentence on the slide. Great, another update that breaks checkout. If we only look at individual words, the word great points in a positive direction, but the phrase breaks checkout points in a very different direction. In context, this is probably frustration and perhaps urgency. This is the main lesson of sentiment analysis. Words are clues, but context decides. A rule-based system might use a dictionary. If the word great appears, add a positive score. If the word broken appears, add a negative score. The strength of this approach is that it is transparent. You can inspect the rule and understand why it fired. The weakness is that it is brittle. The rule does not really understand sarcasm, negation, or domain context. A learned classifier works differently. It can learn that another update, breaks, and checkout often travel together with frustration or urgency. It does not need to trust just one keyword. It can combine several signals. This is not magic. It still depends on the quality of the training examples, but it can handle patterns that are hard to write as simple rules. Modern language models give us another option: zero-shot classification. Instead of training a new classifier immediately, you can give the model a text and a set of candidate labels. For example, positive, neutral, negative, and urgent. The model then chooses the label that seems most appropriate. This is very useful for prototyping. If you do not yet have a labeled dataset, Zero-shot classification can help you explore whether your labels make sense. But it is still a classifier and it can still be wrong. It still needs evaluation. The candidate labels also shape the answer. If the labels are positive, neutral, and negative, the model may return negative. If the labels are bug, praise, urgency, and churn risk, the same sentence may become urgency plus bug. The input text did not change. The decision space changed. So the practical rule is use sentiment as a signal, not as truth. It can help prioritize, summarize, and monitor language. But if the signal drives action, you should test what kinds of mistakes it makes. Before moving on, try a small practice step. Take one sentence from a product review or support message. Classify it once with broad labels, such as positive, neutral, and negative. Then classify it again with workflow labels such as bug, refund risk, praise, and urgency. Compare what changed. That comparison is often more useful than the first prediction. And now we can ask the next question. How do we know whether a classifier is good enough? When people first evaluate a classifier, they often start with accuracy. Accuracy asks a simple question. What proportion of predictions are correct? This is easy to understand and sometimes it is a useful first number. But for many classification systems, accuracy can be misleading. Suppose we build a model to detect customers who are likely to churn, and only 10% of customers are actually at risk. A very bad model could predict not at risk for everyone. It would be correct about 90% of the time. The accuracy would look high, but the system would fail at the task we care about. It would not find the customers we need to help. This is why we use the confusion matrix. The matrix is not just a table, it is a map of system behavior. It separates true positives, false negatives, and true negatives. If the model predicts risk and the customer really is at risk, that is a true positive. If the model predicts risk but the customer is fine, that is a false positive. If the customer is at risk but the model misses it, that is a false negative. And if the customer is not at risk and the model correctly ignores it, that is a true negative. Once you see these four outcomes, precision and recall become easier to understand. Precision asks, when the model takes an action, how often is it justified? If the model says contact this customer, how often was that a good use of the team's time? Precision matters when false alarms are expensive or disruptive. Recall asks a different question. Of all the real cases, how many did we catch? If there are 100 customers who are truly at risk, how many did the model find? Recall matters when missing a case is expensive. There is one more practical detail. Many classifiers do not only output a label, they output a score or probability. Then you choose a threshold. If the score is above the threshold, the system takes action. If the score is below the threshold, it does not. Raising the threshold usually increases precision but lowers recall. Lowering the threshold usually catches more real cases, but it also creates more false alarms. So evaluation is often about choosing the right operating point, not just training a model once. Neither precision nor recall is always the right answer. The right metric depends on the workflow. If a false positive means sending a harmless follow-up email, maybe that cost is small. If a false positive means blocking a user account, the cost is much larger. If a false negative means missing a safety issue or losing an important customer, that cost may be larger still. F1 score can summarize precision and recall into one number. This can be helpful when you need a compact comparison, but it does not decide for you. A single number does not know the cost model of your application. So the better evaluation question is not only, is the prediction correct? It is also, what happens when the prediction is wrong? That question connects the metric to the decision. Here is a simple recipe. First, identify the action that follows the prediction. Second, list the cost of a false positive and a false negative. Third, choose the metric that reflects the more important error. And fourth, inspect real mistakes, not just aggregate scores. This is a useful place to practice. Pick one classification task from your own work. It could be support priority, lead scoring, document routing, or review moderation. Write down what happens after a positive prediction, then write down the cost of a false positive and the cost of a false negative. You will often see immediately why accuracy is not enough. Once the error costs are clear, model choice becomes easier. We can now ask, what kind of model is justified by this workflow? It is tempting to end a lecture on classification by saying, use the largest transformer model you can, but that is usually not the best engineering rule. A better rule is, start with a baseline, measure the errors, and upgrade only when the evidence justifies it. A boring baseline is valuable because it makes later complexity accountable. For example, you might start with a majority class baseline. This simply predicts the most common label. It is not impressive, but it tells you what a trivial system can achieve. Then you might build a TF-IDF plus logistic regression classifier. This is still simple, but it is often fast, inexpensive, and surprisingly strong for stable labels. TF-IDF turns text into a numerical representation. If the text says checkout crashed twice, the representation can give weight to words like checkout, crashed, and twice. A logistic regression model can then learn which weighted patterns usually correspond to each label. This representation does not deeply understand language. It mostly sees counts and weights, but that can be enough when the language is direct and the task is stable. It is also easier to inspect. If the model is influenced by words like refund, cancel, or broken, that may be useful to know. Transformers add something different. They represent words in context. The word sick in "this update is sick" may mean something positive in product slang. The word sick in "the patient feels sick" means something else. A contextual model can represent these two uses differently. So the value of a transformer is not simply that it is larger. The value is that it can capture context that simpler representations miss. This can help when the language is nuanced, the labels are subtle, or the cost of mistakes is high. On the slide, you can also see a small code example. The point is not to teach every line of code here. The point is to connect implementation to measurable output. We fit a simple model, and then we look at results such as baseline accuracy and recall on the risk class. If accuracy is acceptable but recall on risk is poor, that tells us what to improve. A useful habit is to inspect a few mistakes before changing models. Look at 10 false positives and 10 false negatives. Are the false positives caused by angry language that is not actually churn risk? Are the false negatives caused by polite language that still signals cancellation? This small manual review often tells you whether you need better labels, more examples, a different threshold, or a stronger representation. This leads to the trade-off. A transformer may improve accuracy or recall, but it may also increase cost, latency, privacy concerns, and maintenance work. The model is part of a system, so the system trade-offs matter. The practical rule is, define the action, measure the errors, compare against a baseline, and upgrade only with evidence. If a simple model solves the problem, use it. If the errors are costly and the language requires more context, then a stronger model may be justified. This is a very reusable pattern. It applies to sentiment, topic routing, moderation, intent detection, and many other NLP tasks. The exact model may change, but the workflow stays stable. Define the decision, build examples, evaluate the errors, then choose the simplest model that meets the need. Let us close the loop. In this lecture, we saw that labels define the workflow. Examples teach the boundaries. Metrics connect mistakes to cost, and model choice should follow the evidence. That is the core classification workflow: labels, examples, metrics, and models. For the next step, try applying this to one text stream you know well. Choose the labels, write down 3 examples for each label, decide which error is more expensive, and only then ask which model you would start with.